Okay, in this video, I'm going to show you how to derive the formula for the radius of a drop. So what Millikan did was he shut off the voltage and he let gravity make those drops pretty much instantaneously go to their terminal velocity. Okay, so this little drop of oil, if you shut off the electric field, right, this little drop of oil has the force of gravity acting down, well, almost instantaneously, because these things have terminal velocities. These are tiny drops, like a drop of fog mist, right? They're so tiny that they have terminal velocities that are like 10 to the minus fifth meters per second. In fact, if you look up at a cloud on a cloudy day, right, that cloud, all those drops are falling as fast as they can, which is very slow, right? Take them 100,000 seconds to go a meter or something like that, right? So in fact, they might be falling in air that's rising faster than they can go down, right? So this drop at terminal velocity, right? Okay, at terminal velocity, you've got the force of gravity down, and then you've got the force of air friction up. Okay, and these guys are equal to each other if it's at terminal velocity, which it'll reach instantaneously. Okay, 100,000th of a second or something like that. Okay, so this force up we get this from something called the Stokes equation. Okay, the force acting on a small sphere falling through air is equal to 6 times pi times the viscosity of air. We really haven't talked about it. It's similar to friction, but it's not friction, okay? And then the radius of the drop, and then the velocity, okay? What this means, by the way, is that I think it's that big drops fall faster. Once you figure it out, you'll see. And smaller drops fall more slowly, okay? At their terminal velocity, but you'll have to mess with the equation to get that. So this force upwards is our 6 times pi times mu times r times the velocity. This v is our velocity. So don't confuse that v with the voltage that's suspending it. That's a lowercase v. That's our suvat v. Okay? And then we're going to set these guys equal. Remember the mass. Mass is density times volume. I guess I should spell out volume, right? The density is rho, and the volume is 4/3 pi r to the third, because that's the volume of a sphere, okay? So this equation ends up being 6 times pi times the viscosity of air, right, which is something we know, times the radius of the drop times its terminal velocity, right, equals the density times 4/3 pi r to the third, right, times gravity. Okay, now you're going to solve this. You want to solve for r, because what Millikan did was he had an equation. If you recall, the previous equation was q as a function of the radius and the distance separating the plates, the suspension voltage, the density, I can't remember. Is there anything else? I can't remember. But anyway, the radius of the drop was the only thing that we couldn't measure directly. The plates, we could measure how far they were apart, the voltage across them, the density of the oil. All of those things we could measure, but the radius we couldn't measure. So what he did was he shut the voltage off, let them fall. Big drops fall faster, small drops fall more slowly. And this equation got him the radius. From the radius, you could calculate the charge, and from graphing the charge, you could actually determine the charge on a single electron, which is kind of an amazing thing. So solve this thing for r. Don't forget to cross off one of the r's. That should be your first step. And then you'll end up putting all this stuff on that side. It'll be a square root. R will be the square root of a big ugly thing. It's not too ugly. It's kind of beautiful. Okay? So that's what you do. In the next video, I'll show you how to do dimensional analysis for that. Okay?